Our bootstrapping lecture, number 19, was a little bit of a repeat of data 8, but with some new details. We did not concretely analyze the bootstrap in some deep mathematical way. We don't have the probability and statistics tools, at least in our class, in order to do so, but let's talk about what we did say in the class. So it's very common that we want to compute some kind of statistic for a population, like what's the average height of all people, or what's the Tversky statistic for basketball players from homework 5. And ideally what we would do is have the entire population of everybody, like a total census, and compute that statistic. But often we only have samples. So usually we only get a sample, so we might grab 4 people out of all people and compute their average height, second sample, and so forth. And of course, every time we draw such a sample, we get a different statistic. Ideally, our sample mean in this case would be the same as the population mean, but we don't know. So we could draw many samples in order to get a sense of how good our statistic is. That is, we take sample 1, 2, 3, I don't know, 100,000 of them, whatever. And then we could actually plot all of those sample means, and that would give us a sense of how confident we are that those sample means are good. So if we find, for example, that they're tightly clustered around some particular value, then we have a sense, we can actually compute a confidence interval that says, okay, hey, 95% of the samples I drew were between this height and this height. So we feel pretty good that the average height of people in the entire world lies in the middle. Okay. Now where the bootstrap comes in is we observe that often we get a data set and we can't get another sample, right? We got it from someplace and it's in a paper somewhere. Someone recruited students at some university to do something. And there's no way that I can go back and redo that experiment under the same conditions. It's data from the past. Or it could be just that it's too expensive to collect additional samples. And so what that will do, what the bootstrap is all about is if we only have one sample, how do we still get this confidence interval with just that one sample? So the basic idea is we, after we take our single sample, then we will sample from our sample with replacement and compute our statistic, in this case, say, the sample mean, and then, of course, I could build a confidence interval here among my bootstrap samples. And that approach will give me some confidence interval that gives me a sense of how good my statistic is for my sample. Now, this confidence interval itself, we have to think about the quality of the confidence interval, because unlike the previous case where we actually drew a bunch of samples, now we're kind of cheating, it feels like. And so we need to think a little bit about this confidence interval. Okay? So here, what we end up with is this bootstrap distribution. And so what I want to do is focus on the quality. So Fernando did a cute little experiment on restaurant ratings and did an experimental validation of the bootstrap. And the basic idea is this. The average rating of a bunch of restaurants is given here, and this is safety rating, is given here by this red line. That's the average rating. It doesn't really matter what the x-axis is. You can see it's actually clipped off the bottom of the slide, sorry. Oops. And each line on this is another sample. So in this case, we're not actually doing the bootstrap to get each line. Each line is one bootstrap distribution. So I took one sample, I computed a 95% confidence interval for the mean for that population, then I did it for a second, and a third, and a fourth, and a fifth, and so forth. And what we found is that out of 100 samples drawn, 94 of them had the mean in their 95% confidence interval. Now, sometimes it was way over to the right. So in this case, this particular sample that we drew, it says the means are on here, but it says, you know what, it might be anywhere in here. I only have a 95% chance that it's even in this range. And so that would be still considered a success, even though the sample mean is fairly far from the population mean. Now, there's some cases, like this sample, where the 95% confidence interval did not even contain the population mean, but I mean, that's why it's called the 95% confidence interval. It may be the case that, well, there's a 5% chance that my sample is just not good enough to capture the mean. Now, of course, in the real world, remember, you only get one of these blue lines, and this was a bit of an artificial experiment that says, well, let's actually just see what happens if we drew, in this case, 100 different samples and estimated the bootstrap distribution. Okay, So I thought this was a really cool idea. And again, this is only the 2-minute version of it. So if that didn't make sense, go watch the original. Now, some important points. This Bootstrap distribution, first very important point, is that it is centered not at the actual population statistic. So for example, let's suppose we have a population that looks like this. This is the actual distribution of values. And this right here is the sample mean. And to be clear, the y-axis is the density, the number of entities that have a value of around -1. So basically, nobody has a value less than -3 or greater than 8. But it's very popular to have -1, a little less popular around the mean, and so forth. And this is the sample mean of this distribution. So you could think of this as let's say a plot of heights where we have 2 different subpopulations in a community. So the average is maybe in between the average of the 2 subcommunities. So then the sampling distribution here says, if I generate a random sample of, I don't have the number of samples here, but for a number of samples drawn arbitrarily from this population, if I look at the space of all possible samples, this is what I would expect to compute for the mean. So this is the sampling distribution of the sample mean. And then here we see 4 different samples. So sample 1 is I got these 50 people. I think it's 50. These 50, these 50, these 50. And this here shows the Bootstrap confidence intervals. So basically, one of these blue lines from before, this is now looking at it from the side. And so we see that for this particular sample, the sample mean is here, the actual mean is here, and this is the 95% confidence interval would be down between, I don't know, here and here roughly. But this is the distribution of doing a bunch of Bootstrap sampling with replacements and then computing the mean. This is the spread we get right here. And this spread here is drawn, so typically the number we say is somewhere around 10,000 of these, you'll do these samples with replacement. I'm not sure if this was actually 10,000, but I bet, let's see, I can look at that figure. Yeah, I think it was the 10,000. I'll talk about this right column in a minute. And so basically the punchline here is for all 4 of these samples, I mean, we may get different means for each one, but for the most part, the distribution contains the population mean, okay? And sometimes we're off a little more. So this is basically just, you can think of it as 4 rows of Fernando's experiment. Over here, actually, there's this question of how many different bootstraps, or how many samples with replacement should you draw? And this is basically just showing that as we increase the number of samples that we draw from 1,000 up to 10,000, we get a smoother curve. Okay, so this is for r equals 1,000. This is another example of r equals 1,000. So I think these are just 2 experiments side by side. Kind of a weird figure, honestly. And then here, r is 10,000. So we get 2 examples for r equals 10,000, and we see that it's pretty robust and smooth. All right, so the point here, though, the important point is that that distribution you get back when you compute your Bootstrap distribution for the sample mean, it is centered at your sample mean. It is not centered at the population mean, otherwise that would be magic. That would basically be like saying, I'm going to take 4 people at random in the world, and then I'm just going to randomly resample them with replacement, and that's going to give me the average height for everyone in the world. Clearly impossible. Okay? So good point to really drink in and understand is that the Bootstrap distribution is centered at the observed statistic, not the population statistic. Another important point is that the Bootstrap doesn't do really well for statistics where if I have a, say, sample of 10 or 20, that it depends heavily on a small number of observations, like, for example, the median. And what I mean by that is if I only have a small number of samples and I move one value around in the middle a lot, right? So let's say we have all these points in space, and here's the median. If I move the median around, it's possible that I'm swinging the entire value for the median just based on that single value, because if it's the middle point, the statistic only depends on that single point, as long as it doesn't cross any of the others, if that makes sense. So here's the example, again, similar to before, where this is the population of values. So you'll notice it's the same one. And this is the median right here. And this is across all possible samples of size 15. What does the median look like in them? And here is one particular sample. Its median is here. This sample, its median is here. This sample, its median is here. And this sample, its median is here. If we want to get a sense of how good the median is, we sample with replacement from our sample, and we get all of these different medians. And we'll notice some differences from the previous example, which is that first, our bootstrap distribution is discrete, not continuous. So here you go. Like there's no example where the median's ever right here. And hopefully that makes some sense because this point does not appear in my samples, right? So there's no possible way that my median could ever be any value other than the ones that exist. Oh, and the thing I was saying earlier that was a little confusing, right? Let's suppose, let's see, this one right here. For this sample, the median is right here. But if I change just this single value over to the right so that it's here, I've now changed the median, the statistic for the entire population, by that relatively large amount because the median actually only depends on this single value in terms of its actual magnitude, right? So if I move this line around, this value, the median moves with it, which is very unlike in a sample mean situation where if I move just one value, it's only going to change the mean just a little bit. Okay. So anyway, continuing along, the bootstrap, in this case, we get this funny distribution that's discrete, and we'll notice that its shape is very different than the sampling distribution for the median. I mean, it must be, right? It's discrete versus this one, which is nice and smooth. So these are very different from each other, though I'll note that the confidence interval is relatively good, right? So we can think of the 95% confidence interval here as, well, 95% of the samples drawn with replacement in our bootstrap contain the median. Okay, so that's, the confidence interval is actually okay, even though the distribution's a little weird. Now I should mention that the bootstrap can actually do a terrible job. Like the confidence intervals you get back might not actually be any good, right? They were good in Fernando's experiment and in this experiment, but this is a counterexample showing that if we're drawing samples from, say, an exponential distribution, it's actually not that unlikely for this sample size. I don't know if it was maybe, again, we don't have any numbers here, so it's hard to tell, maybe 50. Here, the sample mean computed, so this is an easy statistic. It's the mean. It's not something weird like the median. But even so, because this is an exponential distribution, it turns out that with n equals 50, you end up here having a 95% or even 99 or even more extreme confidence interval that is actually total garbage because the population mean lies way over here. So you could increase the number of samples here and that would fix the problem. I don't know what appropriate n you need to have, but just the point here is that the bootstrap is not a foolproof thing. For a given situation, you need to have an appropriate number of samples to actually get a distribution which is meaningful, and it's a bit of an art. And there's even examples you can construct that are especially pathological, where even a huge number of samples is not going to be particularly great. And so it's good to be aware that the bootstrap is not magic. So hopefully it makes sense what the bootstrap's all about. It gives you a sense of how good your statistic is, but it may be unreliable, for example, for poorly chosen samples. So again, if I only measure a specific subpopulation, I mentioned this I think way earlier, then you're going to get terrible results. So if we only measure the heights of men, but we expect the results to apply to all humans, the bootstrap's not going to help us with that problem, right? We made a fundamental measurement error. Another is statistics that depend on a small number of observations, like for example the median or I don't know the 5th percentile. Samples that are drawn from tricky distributions where the statistic relies on extreme but unlikely values, that can also cause us some grief. And if the sampling distribution is unlike a bell shape. And I don't have any examples really here in lecture, but it was mentioned in the slides, so I figured I'd repeat it here. And if you want to deal with this issue, one way is to take more samples if you have them, and there's other ways to cope with it. For example, assuming a specific distribution and thinking about things in a distribution-sensitive way, but that's beyond the scope of our class, and Fernando mentioned it briefly, but it's not something we've talked about in any detail. And then just wrapping up with a little bit of terminology from the lecture, we mentioned the idea of a Monte Carlo algorithm, which gives a correct answer with high probability, so that's something like these resampling methods. There's Las Vegas algorithms, which were mentioned. Not quite sure why, to be honest, since we haven't used any in this class. But it's a cute idea. It's the opposite of a Monte Carlo algorithm. And that's an algorithm which always gives the right answer, but it may be very expensive in some computational way with some low probability. Now again, we haven't seen any such algorithms in this class, but if you've taken a data structures course, quicksort is an example, where you get a sorted array, but it may be very slow with some small probability. And then lastly, we talked about random number generators. And the important point here, I mean, we talked a little bit about how they work inside, and we may ask some basic question about that on the final. But in this review, at least, all I wanted to bring up is the most important point, which is that it gives you a sequence of random numbers starting from a random seed. So you basically initialize it with some state, and that state is finite. And then it gives you numbers that are spit back at you that are not actually random, but they appear random. And we use that a lot in data science because we want to have some control over randomness so we can repeat our experiments. So if I want to show you that my Python notebook is actually doing the right thing, you can run it on your computer and get the exact same distribution because they're seeded with the same random values. Okay, so that's it for my ultra condensed version of the Bootstrap lecture. And as always, go back to the original source if there's little points that seem shaky. And so that's that lecture. It's kind of funny. I never had to know how to end these. I will see you in the next video. I can't say that over and over. Anyway, see you in the next video.